So we'll start by mentioning that, so now we are discussing the normal distribution, and we start by this, mentioning that this is an example of a continuous probability distribution. And we mentioned earlier that here we calculate the probability. We calculate the probability that the random variable X falls within a given interval. Find, or we calculate the probability that the random variable X falls within a given interval, as opposed to exact values. So here we'll not be dealing with probability that X is something. We'll not be dealing with such. We'll only be dealing with probability that X is either less than something like that, or probability that X is greater than something, can be greater or equal, doesn't matter. Or probability that X is within some interval, like that. So we'll be dealing with that. Okay, so let's consider, so the shape, the normal distribution, is a continuous unimodal bell-shaped and symmetrical distribution. So that's the shape. First, we have talked about the variable itself is continuous. It's not discrete. Then it is unimodal. Unimodal means that it has only one modal value. It is bell-shaped. So here we're just talking about the shape. And also here, it's about the shape. So graphically, the normal distribution curve or graph will look like this. So you have, this is the variable X, and the graph will look like this. The graph will look like this. And here maybe you can say, defined for values of X between minus infinity and positive infinity. So this curve here is defined everywhere on the real number line. It is defined everywhere. So if you look at this curve, maybe it's not looking nice, but this is what we're calling, if you're able to get a line like this, which divides the curve into two equal and identical parts, then that will be the line of symmetry. Okay, then we are saying that this center, if that's the line of symmetry, then this must be the center. That must be the center of the distribution. And if you look at this graph, let's say, let's put about the y-axis here. If this is y-axis, usually this is y, or the probability now on the vertical axis. If you were to look at the vertical axis as what you are calling frequencies, if you are dealing with frequency distribution, this would be, if you look at this as a frequency curve, this is the curve we're talking about, which is now a probability curve. Of course, we know that a probability curve can be coming from a frequency curve. If this was a frequency curve, then this would be the highest point of the curve, this one. And the highest point of the curve corresponds to the mode. So that means the value of x which corresponds to this point, which is here, this must also be the mode. So that center must be the mode. And because this is the center, that means this is half of the distribution. This is 50% of the distribution. And this is also 50% of the distribution. Then this, in addition to being the mode, it's also the median. So this particular point, this point here, corresponds to at least those two measures. It is the median and the mode. Then later on, or it can also be proved that that is also equal to the mean. So the normal distribution is such that the mode, the median, and the mean are equal. We know the location of the median must be at the center. And the mode, we know it's the most probable. In this case, it will be the most probable value of x. So the most probable value of x corresponds with the median value of x, and it's also the mean value of x. So this is a feature which is only true for this particular distribution, which we are calling the normal distribution. So we are saying that this is 50%. The left-hand side, that is 50%. And also the upper side is also 50%. 50% is just half if you convert to decimals. Okay. So we note that the area enclosed by the curve and the x-axis is always equal to 1. That must be satisfied. If this is a theoretical probability distribution, then the shaded area must always be equal to 1. So this area which we are saying is equal to 1 is the same as total probability. If you remember, our probability distribution in form of a table, when you summed up all the probabilities, you are getting 1. So that is the same as what we are calling the area under curve. The area enclosed by the curve and the x-axis is always equal to 1. That represents total probability. So in short, the shaded part is the probability that x, for example, if you look at this point, this dot here, then the part shaded in pink, that is the probability that x is below the mean. And the other part which is shaded in brown is the probability that x is above the mean, which is 50% or 0.5. Okay. So you know from calculus, how do we find the area or the area under curve from calculus? We use a concept known as integration. So if this probability curve here is given by some function of x, there's some formula which is giving us this function of x, which conventionally, instead of calling it function of x, we'll be calling it phi of x, where phi of x just means function of x. But in the context of probabilities, we prefer to replace the f from the Latin alphabet. We replace it with an f from the Greek alphabet. So these two are just the same thing. This is just f of x, but now we call it phi of x in this case. We know that from calculus, if you want to find the area below a curve and maybe above x-axis, you need to do integration. So integrate. So here we're supposed to integrate this function of x with respect to x from -infinity to positive infinity. Once you find that area under curve, this will give you a 1. That will give you a 1. So if you don't want to integrate from -infinity all the way to positive infinity, you will be integrating from a certain point to the other point. For example, if you integrate from -infinity to 0, then phi of x dx that will give you 50%. The area is half. So it's the area from minus infinity all the way up to this point. The area shaded in pink, this will be 0.5. And also we can say if you integrate from 0 all the way to plus infinity of phi of x with respect to x, this will also be half. Okay. So please notice that I've not given you the formula, the explicit formula that we are supposed to be talking about here. But just to have you appreciate the kind of formula that we are talking about, I'll just display the formula. I just Google search, and then I display the formula. Then after that, we can move on. We'll not be using the actual formula here. We'll be doing some transformation to use to obtain a simpler version of the same, which we'll be working with from now or up to the end. So I have shown you the formula for the binomial and the formula for the Poisson. So this is a formula for the normal distribution. And the normal distribution is also known as the Gaussian distribution. And these are the shapes. I think we have already mentioned this. These are the shapes of the normal distribution. But this is a formula that we are supposed to be talking about. The formula, the formula is f of x. F of x just means a function of x. In other words, this is a formula which has x as the only variable. The other parts are constant. So we have sigma, which we know clearly this is standard deviation. This is 2, this is square root, this is pi. You know, pi is 22/7. This is exponent. We have talked about this under Poisson. This is minus half. Then x minus mu. Mu is the mean, and sigma is the standard deviation. Then all that is squared. So this is simply a function of x. But we are saying, instead of calling it a function of x, I'm replacing this f with phi. So this is a formula that if you're talking about integration, this is a formula that this is a guy that we should be integrating. Let me see if I can copy this image and take it to our working space. So let's see if I'm able to post this guy here. So, we are not able to copy and bring that formula here, but we have seen how the formula looks like. So the function that we are dealing with. So this f of x, this is what we are supposed to integrate and get those probabilities. But luckily we will not be doing that kind of integration in this class. So let's look at some of the properties of the normal distribution. The properties of the normal distribution. We're going to list 6 properties of the normal distribution. And then after that, we'll define an alternative distribution, which we shall be calling the standard normal distribution. So there are some 6 properties of the normal distribution that we're going to discuss here. And the first one is about shape, which you have explained, that the shape is symmetrical, bell-shaped, and unimodal. So that means the shape will always be looking like this. That is the shape, such a way that you have a line of symmetry somewhere at the center. This is the center all the time. And this is supposed to go all the way to minus infinity, all the way to plus infinity. This is your probability curve. This is a normal probability curve. The second one is that all the points on the curve are above 0. So if this is your x-axis, is your x-axis, then you can say this is your y-axis. So this is y, this is 0. Maybe this is 0.1, this is 0.2, all the way. So these are probabilities. And we know that the highest value it can be is 1. So on the vertical axis, the highest point we can go is up to 1.0. So we're saying that all the points on the curve are above this line, because this is where y-axis is 0. So every point on the curve is above that line, is above 0, and it becomes closer to 0 as you approach minus infinity, and also as you approach positive infinity. Of course, positive and minus infinity are not actual points that we'll ever get to, but as we move away from the center, in short, the curve becomes closer and closer to the x-axis. But there's no point in time when this curve will ever touch the x-axis. It will never ever touch the x-axis. It will only become closer, but it will never ever touch. So that's the second. Then the area enclosed by the curve and the x-axis, this area here is 1. Very important. And we're saying that mean is equal to the mode is equal to the median. So this point here is your mu. That point there is your mu. Maybe I should have said here, the normal distribution is a continuous, unimodal, bell-shaped, and symmetrical distribution defined for values of x between plus and minus infinity. And this is also fully defined. Maybe I'll say that later. So I needed to say that the normal distribution is fully defined by some 2 parameters. Mentioned that there are 2 parameters. U stands for the mean, and sigma, or sigma squared, but I'll use sigma, which stands for standard deviation. So for the normal distribution, we need to know those 2 parameters, mu and sigma. So this is the first parameter. The first parameter is equal to the median, is equal to the mean, is equal to the mode, mu. Then the second parameter is given by the standard deviation of x. This is the standard deviation of x. This is mean of x. So if you're given a variable, a random variable x, its mean is what you're calling the mean or median and mode in this case. And if you are able to find the standard deviation, and that would be the sigma of your normal distribution. So that's the fourth property. Then how do you find the probability that x is within some given interval? For example, x is between x1 and x2, of course, where x1 is less than x2 in that case. So how do you find such an area? I mean, that probability. You find the area under the curve above the x-axis, but between the ordinates at x is equal to 1 and x is equal to 2. So if you consider this curve like this, then that vertical line there, this is mu. That is what we're calling the ordinate at x is equal to mu. This is the ordinate. Ordinate at x is equal to mu. So if you have a point here, let's say x1, that light should not be crossing the curve. So this vertical line there, if this is your x1, so this is the ordinate at x is equal to x1. Then you can have another point here, let's say x2. This is the ordinate at x is equal to 2. So if you want the probability that x lies between x1 and x2, we are looking at that area. The area below the curve, above the x-axis, enclosed by the ordinate at x is equal to 1 and the ordinate at x is equal to 2. So that's the area. So if you were to use calculus, we'll just be doing integral from x is equal to x1 to x is equal to x2 of that function that we saw on Google with respect to x. This is the probability that x lies between x1 and x2. But don't worry, we'll not be doing this in this class. We'll be doing something else which is easier. So that's how you get the probability. And the probability is just the area under the curve between the ordinates at the given points of x. Now, property number 6 is very important. So we say number 6, if we define a new variable z by this formula. So we use x and we use mu and sigma. If we define a new variable like that, then the new variable has exactly the same distribution as x for every pair of mu and sigma. For every pair of mean and sigma, then this variable, which has this simple formula here, remember we were having some formula somewhere, long formula somewhere, which I don't want you to remember for now. But I was saying, but let me take you back there. Maybe you'll appreciate something about that formula and what we are trying to say here. If we go back there, if we go back to Google, I want you to pay attention to this part. Pay attention to this part, the part in brackets. The part in brackets is x minus mu over sigma. So basically what we are trying to define on the other side is actually part of this formula here. So later on we'll realize that what we are defining there is a special type of the normal distribution. So because as you can see, we're extracting that formula from here. So there must be some relationship with what we had seen here. But for now, let's just continue. So we're saying that if you define a new variable z using that formula, then the new variable has exactly the same distribution as x for every pair of mean and sigma. That means that if you have x like this, then you can also have exactly the same. My shapes are not similar, but now instead of x, now I have a z here. So I'll end up with symmetrical distribution, where we said this one was mu. When you're using x, the center is always mu. But when I'm using z, mu is 0 and sigma is 1 always. So now this changes to 0. And you see, even when we're using x, mu can be 0. It can be 0 because we say that x takes any value from minus infinity to positive infinity. So mu can be 0 when we are defining the function of x. But we are saying that now z is a special type of normal distribution where the mean is always equal to 0 and standard deviation is equal to 1. So here z gives us the number of standard deviations a value is either above if positive, if the number is positive, it tells you the number of standard deviations above or below. That is if below, sorry, if negative, the mean. The number of standard deviations a value is above the mean. For example, if a z is 2, if z is equal to 2, this means that 2 standard deviations above the mean. If you have z is minus 1.8, it means that you have 1.8 standard deviations below the mean. So for example, you can have, that is 1 standard deviation above the mean. There are 2 standard deviations above the mean, 3 standard deviations above the mean. Then in a similar way, you can have 1 standard deviation below the mean, 2 standard deviations below the mean. And you can also have 3 standard deviations below the mean. You will realize that when we're dealing with this new variable here, I think I need to give it a name. So we say that here, z is called the standardized value of x. So this z is known as the standardized value of x. It is actually a transformation of x. It is just a transformation of x, which we are saying has exactly the same distribution as x. So z and x have the same distribution, exactly the same distribution. Have exactly the same distribution. So instead of calculating probabilities using x, where we require to do integration, we can quickly compute the same probabilities using z, which in this case will not require integration. Of course, somebody has integrated for you. Okay, so this is how you interpret the z values. They tell us how many standard deviations are above or below the mean. How many standard deviations are we below or above the mean? So this is how we apply z, application of z. Which we call standard normal distribution. Standard normal distribution. So the distribution of z is known as the standard normal. So this one is just the normal distribution, the one that we've been discussing. But if you confine your mean to 0 and sigma to 1, this is now called the standard normal. And the area below here is always equal to, the area will always be equal to, so nothing changes. 1, 0. So this z has all the properties listed from number 1 to number 5. But in addition to that, we have this additional property that mu in this case must be equal to 1. So when you come here, you say that this one must be equal to 0, and this one must be equal to 1. That's the only difference. The other parts are the same. The other parts are the same. So you just come here and replace where there is x, you put z. You put z. Here you put z. Here you put z. You put z. You put z. Because z is a transformation of x. So all the properties listed from number 1 to number 5 are correct. Okay. So now how do we apply this? How do we apply this? So let's start by saying that let x be a normally distributed random variable with mean mu and standard deviation sigma. The probability that x lies between x1 and x2 is the same as the probability that z lies between a z1 and a z2. So in most of the cases, questions will be asked in terms of x, but we'll be transforming that x into a z, where x1, what is that? Where x1 is, where z1 is x1 minus mu over sigma, and z2 is x2 minus mu over sigma. Already we are given mu and sigma. This will always be given. This will always be given. Now, this part here, we said that this probability is obtained through integration. This is a mathematical approach. But luckily, here, we use tables to obtain the probabilities. So here, there'll be no use of integration. We just read the probability values from some tables, which are known as standard normal tables. Standard normal tables, which I'll be showing you in a short while. Okay, so for example, let X be age of students in a class. Then we assume X is normally distributed. When you mention that X is normally distributed, you must mention mu is what? And let's say standard deviation sigma is 4, for example. Let me use 2. So if this is the question that you have, you are told that the age of students in a class is normally distributed with mean 20 and standard deviation 2. Somebody might ask you, calculate the probability a student chosen at random is, let's say 25, let's say is 25 years or above. Let's say is less than 25 years. That is less than 5 years old. So you calculate that probability. Okay, so basically what this question is saying, and this will not be doing this, we are saying that there is X there. Then we have this curve here. Then the mean, which is at the center, is 20. Then there is a 25 somewhere. The question is, when the probability that this guy is what? Is less than 25 years older. So we need this probability here. We need this area. Less than 25 means I have that. If we are using calculus, we'll be integrating function from minus infinity to 25. But we are saying this one can be expressed in terms of Z. Okay. So Z will have the center as 0 all the time. And it also starts from minus infinity to positive infinity. Even this one, plus infinity all the way to minus infinity. So what we need to do is to find which value of z here, which you can call z1, corresponds to this value of 25. So that's why we need to transform. That's why we need to use this transformation here. We need to use that transformation. So we'll come here and say probability that the age is less than 25. So here I'm also supposed to shade like this. We're looking for the same. Is the same as probability that z is less than z1, where this z1 is x, which is now this value here, minus my mu, which is given in here, which is 20, divided by my standard deviation, which is 2. So that will be my z value. Which is 2.5. So that means that this point here is, so we're talking about 2.5 standard deviations above the mean. We need the area below there. We need the area. So we need the area, the shaded area here. This area is obtained from tables. This area is obtained from tables. But even as we go to the tables, we know the properties of this curve. We know that the area from wherever it is coming from, that is minus infinity, all the way up to that point, we know that area is half. Is half. We say that up to 0, that is center, that is 50%. So we know this probability must be 0.5 plus something else. So we need to get the other portion. We need to get the other portion. Okay, but let's see how the tables will look like. Let's see how the tables look like. So we're going to adopt a certain type of tables where only areas from 0 up to a point, let's say a point like Z1, a point Z1 standard deviations above the mean. So the tables that we're going to use will be giving us the area from the center up to a point like here. Because it is obvious, if you need the area from 0 all the way to minus infinity, that is a half. And the area from 0 all the way to plus infinity, that is also a half. So if you get this area here, if you get the area that is now shaded in black, let me shade it again. If you get this area, if you get this area, then you can get any other area that you want. You can get the area above Z1, you can get this area. Because if you know the area from here, 0, all the way to plus infinity, if you know that is 0.5, and you are told the area from 0 up to this point is maybe a certain number, then it is easier for you to find the unshaded part. The same case, if you need the area from Z1 all the way to minus infinity, you know how to get that, because the area from minus infinity up to the center is 0.5 plus this one, which you'll always get. So I guess now it's visible. I'm sharing the standard normal tables, if I'm not wrong. So there's this narration here, which says, the table gives the area under the normal curve. Now we are aware that area under curve just means the probability between the mean. We said the mean is the center all the time. And in this case, this is our mean. Our mean is 0. And a point, which is Z standard deviations above the mean. So this is the point we're talking about. You can call it Z1. You can say Z1 here. And a point Z1 standard deviations above the mean. So there are other tables which will give you this area, that one. So this is 0, this is Z1. So they give you the cumulative area from minus infinity to a point Z1 standard deviations above the mean. Other tables will give you this area. Sorry about the shape. 0, so they'll give you Z1. So they'll give you the cumulative area from minus infinity to a point Z1 standard deviations below the mean. Others will give you the area above. Okay, so if this is Z1, like that. But all the same, all the tables talk the same language. They mean the same thing. So you just need one table, then you can extract whatever probabilities you want. But I think this is one of the best. Just you are given a point above the mean, and we're given the area from 0 up to that particular point. So if you want the area, if you want this area here, you will take 0.5, which is the area from the center all the way to plus infinity. You take away the shaded area. If you want the area from Z1 going up, this one you get directly from tables. This one you get from tables directly. So if you want to get corresponding areas below the mean, for example, if you have a point here, this would be minus Z1, for example. You can call it minus Z2. You apply the property called symmetry. You apply symmetry. So if you're looking for, if this is Z is minus 2, you just check for Z is equal to plus. So that's the property of symmetry. So instead of having as a table with positive Zs, negative Zs, and so on and so forth, we just use positive values of Z. But in case you want to use to check a negative value of Z, you just apply symmetry because this area is the same. For example, if you have the area from 0 to 1, for example, that area is exactly equal to the area from 0 to minus 1. Exactly the same because of the property of symmetry. So if you know the area from 0 to 1, you also know the area from 0 to minus 1. If you know the area from, let's say, 0 to 2, this is 2, and this is minus 2, and this area is the same as this area, and so on and so forth. So you just need to check the positive and you are done. So our tables are as explained there. So now, if you look at our question, we were looking at the probability that we were looking at this probability. Let me write it here so that we're looking at probability that Z is less than 2.5. So we're talking about a point here, 2.5, and we're saying less than. So less than means you shade here and also here. But we have said that tables will give you this area only because the other part is obvious. That's the reason. Because like the part now that is shaded in red, we know that that area must be 0.5. Then the part that is now shaded in the part enclosed in green, this part here, you check it from the tables. So you go for a value of Z. Z is given in this column, and you can see the formula of Z is as we have given in our notes, or sigma. So this is 0.0. Usually it's written 2 decimal places. So you look for 2.5. So it's 2.50. 2.5. So the value of Z is 2.50, which is there. And this is the value. So 0.493. So this area here is 0.4938, which you must add here. It will give us 0.9. 9938. So that is the probability. So let's go back to the question. If we go back to the question, so we are saying that the probability that Z is less than 2.5, that's what we're looking for, is 0.5 plus 0.4938, which is 0.9938. So we're saying that probability is quite high. There's a very high probability that a student who is chosen randomly from that class is aged less than 25 years old. So this area here, as you can see, the area is more than half. The area is more than half. Okay. So that is how you transform X into a Z. I want you to try some examples here. You find the following probabilities, and then I think we can stop there. If you, then I can answer any questions that will be coming from you. So now that we have seen how Z is calculated, and the process of obtaining Z is not very difficult, I want to spend time trying this. Try to obtain these probabilities. Z is less than 1.87, Z is less than minus 1.23, Z is greater than 0.54, Z is greater than minus 2.34. And the last one, probably that Z lies between minus 2.34 and 1.28. So try those 5, and then you can share your answers with me via the class WhatsApp group. So that marks the end of our discussion. Let me know if there are any questions which we can answer offline.